Now we are going to move on to eventually get to geodesics, but the first thing we need to talk about is parallel transport. So in a flat space, here's our flat space, and we have some curve on that flat space. And you could imagine starting with a vector at some point on the curve and walking along the curve, like someone's telling you to, hold this delicate thing and it needs to always point in the same direction. And you would know how to do that. You would just keep it going up, right? There's not really any ambiguity. So this is what we mean by parallel transport of the vector. You just keep it going in the same direction. Now, when I say those words, I've used the fact that in a flat space, like we emphasized at the very beginning of the course, and again when we defined vectors, in a flat space, you have an isomorphism, a natural way of identifying points in the space itself with the tangent space of the point. So you can sort of view all the tangent spaces as the same. You can identify different tangent spaces. There's one notion of vectors pointing in a given direction, irrespective of where they are on the plane. And so because of that, you can do this in flat space-time. The rule is you just keep the components the same. Keep the components of the vector the same, as long as you're in Cartesian coordinates, or more generally in the Lorentz frame. And so you can do that, and no one ever really thinks of that as remarkable or anything, but it's a very special property of a flat space. In a curved space, we don't have a way of identifying vector fields at one tangent space with vector fields at another tangent space. It's a similar statement to we don't have displacement vectors pointing from one point on the manifold to the other. But we still ought to have some notion of parallel transport, because after all, curved space is locally flat. And if I told you to walk carefully out the door or something while pointing your pencil in one direction and keeping it in the same direction, you'd be able to do that even though we're on a curved manifold here, the surface of the Earth, right? So there has to be some way of characterizing parallel transport on a curved manifold such that it'll agree exactly with what we would have meant in the approximation that we're on a flat space here, but will continue to give predictions over regions where the curvature is non-negligible. For example, if I asked you to hold your pen in one direction while walking halfway across the US, then you would have to think about curved space parallel transport. Kush, did you have a question?
So do we have to keep the direction also same, like the components and the direction of the vector?
Well, the components are the direction, just the xy components that has the magnitude and direction in it. So we need to figure out how this is going to work in curved space-time, and before we make it precise, a good example to think about is the sphere, because you can sort of see on the sphere that things may not be so simple, and there may be some interesting phenomena associated with parallel transport. So for example, suppose we make a triangle with 3 right angles. Say that again, a triangle with 3 right angles. That's the kind of thing you could do on the sphere. And so we're going to maybe draw that in red here. So we go from the North Pole down to the equator along some longitude line. Then we go along the equator for exactly pi over 2. And then we go back up along the next longitude line to the top. So there's our triangle in a sense with 3 right angles. I call it a triangle because all of these curves are great circles. They cut the sphere in half, and as we'll see, those are the straightest possible curves, in the sense we'll define the geodesics. But for now, just imagine I drew this path, and I carried a vector around it. So we can imagine starting with the vector pointing north here. And as we keep it pointing north, it will kind of end up this way. So far, so good. Now, as we keep it pointing tangent to this line as we walk, so it's kind of going out like that, and then we keep it as we go like that, and you can see that at the end of the day, we come back to a different vector. So we went around this loop, we parallel transported it, and we got a different vector from the one we started with after parallel transport around a closed loop. And in fact, one way of defining the curvature of a space is exactly this little experiment with closed loops. If you just imagine doing a small closed loop near a point, the extent to which your parallel transported vector does not return to the original vector at second order in the displacement around the loop, kind of like the commutator problem you did, characterizes the curvature of the space. Okay, but for now, this is just a motivating cartoon to keep in mind for why parallel transport might be an interesting thing to think about for curved spaces. Yes?
We have to keep the vector same, right? Like the same direction?
Locally.
Kind of rotate, right?
It looks like it rotated on the screen, but I claim if you did this on the surface of the Earth, it would, and parallel transported it, this is what you would do. Right? You're keeping it the same direction in the room. It never points off the sphere. You're not using three-dimensional space. You're just holding it like this and walking. So there's no rule that says if you keep doing that and come back to the original place that the vector will be in the same direction. Yep?
This is a weird question that I can't come up with an answer to. At the North Pole, how are you describing the orientation of the arrow? Is it because we're in a flat?
Well, it's tangent to the sphere, right? You agree with that?
Yes, it's definitely tangent. And locally, you can just say it's pointing that way.
Yeah.
But could you, or do you even need to describe the orientation with respect to the sphere overall? Like, I can say it started pointing north. As you go up that second leg, it's pointing north, 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 north. And then when you move on to the third leg, suddenly you're pointing west. Right? You can talk about it with respect to the overall sphere.
Yeah, but
the important part that is we're pointing that way locally.
Yeah, we can use north. We can use cardinal directions, and the point is if you start going north and you walk around a big triangle, just holding it parallel to itself, you'll end up west.
Yeah. I have no issue with that. I'm just wondering, at the North Pole, do we even care about the transition from pointing north?
There's no transition at the North Pole. Oh, you mean the cardinal direction flips? Well, that's because the cardinal directions are singular at this point.
Okay, that's what I was trying to get at.
Yeah, and that's related to the fact that, maybe I shouldn't have picked the point where our usual coordinate system is singular to illustrate this. But yeah, that's a pure coordinate effect. Understood, yeah.
Cool.
Yeah.
Thank you.
Anything else? Okay. So let's figure out what the math of this might be. And this is the first of many times we will use the trick of writing things using our flat space derivative, which was just the partial derivative in Cartesian coordinates, and then making it covariant by replacing that with a covariant derivative. So remember, in flat space, or time, space-time rather, we just kept the components constant, right? So we keep the components of some vector v mu constant. That was the rule, as long as they're Cartesian coordinates. So how can we write that a little more nicely? And here's our curve, here's our vector. Our curves are always some x mu of lambda. And to keep this constant along the curve means d by d lambda v mu equals 0. That's our flat space-time law. And now we're just going to write this in a notation that's ready to send our partials to our covariance. So we're going to remember that this v mu, this d by d lambda, is just the tangent vector t mu contracted with the partial vector, right? Because T mu was dx mu d lambda. And in this form down here, this is just the chain rule. So this equation, d by d lambda v mu, can actually be written, I need a different index, t nu, partial nu, v mu. Okay, now that's kind of nice because now we have this partial derivative, which we know how to promote. We argued that the thing that reduces to the partial derivative in flat space but plays nicely in curved space or in flat space with curvilinear coordinates is the covariant derivative. So we just do that. So promote partial to triangle. And then what's the law? Well, we get T nu covariant nu v mu equals 0. And another way of writing this, which is a little nicer, is to define capital D d lambda v mu. And capital D by d lambda then is just what we needed here. So the tangent vector contracted with the covariant vector. So let's write that as T nu. Oops.
And so this corresponds to like a trajectory that only curves because of the inherent curves?
No, this is any trajectory. We're parallel transporting this vector along any curve. And sorry, what I meant to write here was just plug back in for T nu so it doesn't look so obscure. Dx nu d lambda del nu. And the reason it's nice to think about this as an operator, this makes you realize that it's just a derivative operator along the curve. You know, even though I've written it in terms of this covariant derivative operator, which could act in any space-time direction, it's being contracted with the tangent vector to the curve. And so it really only acts in the direction along the curve. Okay, so this, what we've done then is we promote the partial derivative to the covariant derivative, which is the same thing here. This is d by d lambda goes to capital d by d lambda. And this is going to be our equation of parallel transport. And this will be what we mean when we say you've parallel transported v mu along this curve, x mu of lambda. And that corresponds to the instruction that you keep your pen pointed in the same direction as you walk. More generally, any tensor T with any number of indices, let's just say this one is parallel transported if this capital D by d lambda T alpha beta, let's not use lambda again, call it alpha beta gamma, equals 0. But somehow the vector is the most interesting case. Another example of a parallel transported vector in space-time is the direction that a gyroscope points. Right? So if you're out in space and you have a floating gyroscope, it's going to keep a fixed orientation in space. Right? That's the whole idea of a gyroscope. You use these to figure out which way your spacecraft is pointing, because the gyroscope is a fixed reference. Well, that's something that shouldn't change its direction, right, as you move through space-time. So the gyroscope, the vector, which is a space-like vector representing that gyroscope, is going to be parallel transported along your world line. So, some years ago, Gravity Probe B finally measured the lens tearing precession, which is the idea that if your gyroscope is parallel transported according to the gravitational field, the metric, it feels that, which is different from what you would expect if you didn't have any gravity, and so that's described as an anomalous precession of a gyroscope, and that was measured.
Sorry, where was it measured?
The precession of a gyroscope relative to how it would behave if there weren't any gravity.
So when and where? Like,
Oh, when? There was a mission called Gravity Probe B that is not a great example of a mission, but it did eventually do the measurement it was supposed to do thanks to some last-minute funding from some Saudi prince or something. It was a very strange story. I mean, it was a debacle of a mission, but it did make the measurement in the end. Yeah?
So it is possible to parallel transport something around, like the curve on the sphere you defined earlier.
Mhm.
It just won't look like we're holding it in the same direction from our perspective.
Well, locally it will. At every point as you walk around, you'll believe you were holding in the same direction. But if you marked a line, a red line on the floor here for the direction you held it initially, then you walked around a big loop on the sphere, just keeping it in the same direction, you'd come back here, you'd find out you weren't pointing along that red line.
Okay.
And you would think, did I screw up? No, you were just on a curved space.
Okay, so that is parallel. So you can parallel transport something that happen to be different.
That's right, and that's a signature of curvature. We're going to get an equation that shows you that.
Okay.
So like we just change the partial like the coordinate derivatives to covariant derivatives.
Mm-hmm.
We should also have the connection term, right? Like
It's in there, but I'm not going to write it because that's for calculations. This is for understanding the physics in a nice language. So if you expanded out this equation of parallel transport, maybe that's worth doing to show you how that works. So in some coordinates, to do some calculation, we could write d by d lambda v mu equals, and then our definition of d by d lambda was dx nu d lambda covariant acting on v mu. So dx mu d lambda comes out front, and then last time we derived that covariant is del nu v mu plus gamma mu nu alpha v alpha. And so this thing equals 0 is a definite equation that you could solve, right? It's just got normal derivatives of coordinate components, usual derivatives of coordinate components.
does that X have a mu on it?
This should say nu. Thank you. It's so much better when you guys catch my mistakes. When I make these videos at home, because I didn't like the way it was in class, like a 20-minute video takes me 2 hours because I watch it and I'm like, I wrote mu, not nu. So then I redo it.
Is the first dx, is that supposed to be nu?
This is a nu, yeah. That I wrote, but just not clearly.
Does calculation mistake increase as age increases?
Eventually, but I think I've always been bad at it. My wife certainly complains when I tell her, one thing and think a different thing. So she knows best.
Older.
Wiser, older and wiser. Any other questions? Okay. One nice observation about parallel transport is it preserves inner products. Okay, so the idea is we have a curve here, and now we have two vectors on it. So say the red one is that way, and the green one is that way, locally on some curved space. Now it could be that the space is curved, so there's significant parallel transport, so that by the time you get over here, the red one has moved a little bit according to our coordinates, but then the point is the green one is going to move too. And they're going to just preserve the angle between them. And I'll show you that mathematically. And as a consequence, it also preserves length. That's the inner product of a vector with itself. So let's see this mathematically. Let's say the red one is V, the green one is W. What we want to compute then is d by d lambda of the inner product g mu nu v mu w nu. So we expect this to be 0. That'll be the statement that the inner product is preserved along this curve parameterized by lambda. Now, you could use the Leibniz rule, absolutely.
Should it be d lambda with the big D on top?
That's what I'm about to say. So no, it should be little d because we're just talking about how this number moves along the curve, changes along the curve. But because it's a scalar, we are freely allowed to replace, right? Remember, partial derivatives and covariant derivatives agree on scalars, del nu f. So the same thing is true, d by d lambda of f equals capital D by d lambda of f. So let's do that as our very first step. D by d lambda, g mu nu, v mu, w nu. And then again, we have just the same Leibniz rule from the fact that the covariant derivative was defined to satisfy the Leibniz rule. This capital D, which is just, remind you, the covariant derivative contracted with the tangent vector, will satisfy the Leibniz rule. And so we can just break this up into 3 terms. D by d lambda g mu nu times v mu w nu plus g mu nu d by d lambda v mu w nu plus g mu nu v mu d by d lambda w nu. And now what do we do? Well, by the assumption of parallel transport, so this red one is parallel. So this is 0 by assumption that V is parallel transported, right? That's the definition of parallel transport. This one is similarly 0 by assumption that W is parallel transported. And then what about this last term? What should we do with that?
0.
Why?
Like the metric is just a constant.
Right. Well, careful with the language. You're absolutely right, but don't say the metric is a constant. Say the covariant derivative of the metric is 0, right? Because it could be in a space where the metric changes all over the place, right? But right, so because we find the covariant derivative to satisfy del nu GAB equals 0, it's going to be true that capital D by d lambda d alpha beta equals 0. But getting back to Evan's question, it's absolutely not true that little d by d lambda GAB equals 0. The metric could definitely be changing. So the first thing we needed to do at the beginning of the calculation was flip d by d lambda to big D, which we're allowed to do because it's acting on scalars. If we had left it as little d by d lambda, we could have used the Leibniz rule and expanded everything out, and then we would have had to dive into a mess of Christoffel symbols to see that everything actually vanishes. So the covariant derivative notation is much more convenient when you're doing general manipulations. So indeed, this is 0 by metric compatibility. Compatibility. Okay? And so that proves the assertion that parallel transport preserves inner products.
So it's with a capital N. Like
That's-
even
yeah.
then it's a scalar, right?
We gotta prove 3.
Well, on a scalar, then we can freely interchange them,
That's why
yes.
Above we just replaced it. But
Above, we took one equation holding in flat space in Cartesian coordinates, and we promoted it to an equation that holds in curved space by replacing one with the other. You can't go back. You can't take a curved space and replace the covariant derivative with a partial derivative. That would totally depend on what coordinate system you chose. So it's not giving you anything interesting.
But how can you just remove it
It's a definition if you like.
from flat to curve?
Yeah, I'm motivating the definition of parallel transport in curved spacetime. OK, so just to have it written down, someone asked this, but in particular, parallel transport preserves length, right? So d by d lambda of g mu nu v mu v nu equals 0. It's just the special case where v equals w. So now I'm ready to tell you about an absolutely key concept in the theory of general relativity, which is a geodesic curve. And a geodesic curve can be defined in a few different ways. And I think the most natural one is with parallel transport. So I use the example of holding your pen and walking around on a curved surface, keeping your pen straight. Another thing I could ask you to do is to walk around on a curved surface in a straight line. And I'm not going to tell you what I mean by a straight line. I'm just going to say just walk straight, for a long time, such that you're definitely probing the curvature of the Earth, but you're just walking straight. Now, it turns out humans are really bad at this. If you ask humans to walk straight, they end up going in circles. It's hilarious. But you could imagine just driving a car with like a fixed axle, right? You just go straight, press the gas, and just go. And that'll give you a notion of a kind of straightest possible curve. Which is the one where you just go straight locally. And another way of saying this, someone might say, well, what do you mean by that, right? Well, it's like just go in the direction you're pointing, right? Don't rotate, right? Just follow your nose. Don't rotate. Just keep going in a straight line. So these are all various motivations for the definition we're going to give. And what vector represents the direction your nose is pointing when you're walking?
Depending on where you look, tangent to the vector.
Tangent. Yeah, if you're looking straight ahead. That's right. It's the tangent to the curve, right? So it really means just keep going along your tangent. So whatever direction you're pointing in, that's your tangent vector. Just keep going in that same direction. So what does that mean, to keep going in the same direction? We just talked a bunch about keeping a vector field in the same direction. Yes?
I think would be start out with some vector in the direction you want to go, move a little bit in that direction,
Yeah.
and let that vector parallel transport and keep determining your direction.
Right. Exactly. So to keep going along your tangent vector, well, the direction you're going is your tangent vector. So to keep that direction you're going the same as your old direction, your old tangent vector, you have to keep your tangent vector the same. You have to parallel transport your own tangent vector. So there's actually very little logical leap from one of these statements to the other. But this is the idea, and we've now actually arrived at a mathematical definition because we know what the tangent vector is, right? Its components are, dx mu d lambda for your curve x mu of lambda. We spent a lot of time making that precise and arguing that this is the right thing. And we know what parallel transport means, right? It's no, over here it's little d. These are not tensors. These are just coordinate functions, defining the tangent vector in terms of components in terms of a coordinatization of the curve. But over here, we have big D d lambda, parallel transport something, v, but now it's going to be t. And that is the geodesic equation. Now, there's one point about this that is sometimes a matter of definition. But what you could do is also rescale your tangent vector, right? Make your nose longer, if you like, in this analogy, right? The notion of a direction doesn't care about the length. Okay, so more generally, it's clear that you'll get the same curve if you instead just demand d by d lambda t mu is proportional to t mu. Okay, and this has a name. There might be a problem, or it might not be, depending on problem on the homework. I don't know if I'll have you explore this or not. It won't play a main role in class, but you'd get the same curve. This equation defines the same curve with a different parameter representing it.
So it's basically like you're going on the same path, but your speed is changing.
Your speed relative to your parameter, yeah. But in relativity, the parameter is really going to not be a physical thing. I mean, sometimes we'll choose it to be proper time, but in general, it's arbitrary. And so there's no physical speed associated with parameter derivatives. So this red thing here also captures the idea of just keep going in the same direction. It's just in this last step here, we went to full parallel transport as opposed to just preserve the direction but allow the length to be arbitrary. So this version here, if you like, is the affinely parameterized geodesic equation. Affinely parameterized geodesic equation. And this one is worth writing out in coordinates. This is an equation you have to solve if you want to do physics and general relativity. So freely falling bodies are going to follow time-like geodesics, and light rays are going to follow null geodesics. It's a very important equation. So let's write it in a few different forms. You could also expand out the d by d lambda. So you could write it as t nu covariant nu t mu equals 0. That's the same equation. It's just the definition of d by d lambda with a capital D. Or you could write it out again in coordinates. So let's do the calculation over here in green. So we're going to write t nu, and we have del mu t mu. So it'll be del nu t mu plus Christoffel symbol mu nu. No, we decided not to use lambda. Let's use alpha t alpha. So that was our, so now I've just expanded the covariant derivative. And then the nice way of writing this is to remember that the tangent vector does have a nice formula in terms of coordinate components, dx mu, d lambda. And so we can write this one as dx nu d lambda del nu t mu. That's the first term. And then the second term is the Christoffel symbol, nu alpha, now with 2 copies of the tangent vector, which I'm writing out as dx d lambda. And now we notice that this thing is finally just the ordinary little d by d lambda by the chain rule. This t mu I forgot to expand, so I'll just point out that it is dx mu d lambda. That's just this formula. And so we have an ordinary lambda derivative of an ordinary dx mu d lambda, which is just d2 x mu d lambda squared. So a third and most explicit form of the equation here, I've written out in green, it's two terms. The first term is just the second derivative, dx mu d2x mu d lambda squared, and then this Christoffel symbol term, and I'm going to relabel the indices alpha beta, dx alpha d lambda dx beta d lambda equals 0. Okay, so three forms of the affinely parametrized geodesic equation that you may find useful in different circumstances. Any questions? Just ask.
What do you mean by affine?
I'm not sure where the name comes from. I mean this equation, the black one, not the red one. The red one is a non-affine parameter. Yep?
What exactly is the red one?
It's a different equation for the same curve. Right? The curve is the collection of points as a function of lambda. The tangent vector along the curve can have any length. You can change the length of your tangent vector by changing your parameter, right? Because the tangent vector is defined as dx mu d lambda. And so the black one assumes that the tangent vector's length is fixed along the curve. So it's a very specific choice of tangent vector. And we call the associated parameter an affine parameter.
So when we say it's proportional, because for parallel transport we need it to be 0, right?
That's right. So the red one, the tangent vector is not parallel transported. But that's still, if you solve that equation, you will still get the same geodesic curve. If I give this homework problem, the homework problem I will give is to start with the red equation and show that you can always find a new parameter such that the black equation is satisfied. That's one way to see directly that they're the same equation, or that they define the same curve. To me, when I learned all this, the reparameterization stuff was very obscure, which is why in the first week of the course I asked you guys to actually reparameterize a curve. I don't know if you remember doing that, the accelerating one. So if this looks mysterious, go look over your homework from the first week, and it should start to look a little more clear.